So good morning, everybody. I hope you had a beautiful evening yesterday. Enjoyed the beers, probably not too much because otherwise you wouldn't be here. I guess we have lost some people in the meantime. But for those of you who are here, great that you are here, because now we're going to look at Open SoC Debug, which is of course the perfect thing to do after a couple of beers. First of all, what is Open SoC Debug all about? So it's a specification, first of all, and a specification to do a debug and tracing architecture. That's kind of the first thing. So commercial tools or things that you could compare it to is, for example, ARM Core Site, for those of you that have heard of, or Nexus 5001, which is also a specification in this regard. It's combining debug and trace, and we'll get to that in a second. It's kind of having a common infrastructure there, and it's also a host-side API to plug in tools that make use of this debug and tracing infrastructure for your system of chips. So, for example, in traditional tracing systems, you have your Lauterbach or Keil debugger in a debugging scenario, which is kind of breakpointing and things like that. You have your GDB and things like that. All those tools, of course, need to have access to the device. So we have an API there. Then it's also not just a specification, because specification in paper is pretty boring, at least not helpful to the end user, that is us. So we also have a reference implementation consisting of software and hardware parts. And in the end, it's also a collaboration, and it started between things that we had at TU Munich and at Low Risk, so that's University in Cambridge, or was back then. And initially, we also had a bit of kind of work done by Pulp, and I think that has shifted now back. Maybe we get them back in the future. So that's, I think, what Open SoC Debug is all about. I presented Open SoC Debug, or about Open SoC Debug, already a bit last year. So what happened since then? The specification is constantly growing. We're adding new features, fixing bugs in the specification, rewording things. We had a lot of fixes and new feature in the hardware implementation, and we did a complete rewrite of the host software, and that's probably what I will focus on most in the next couple minutes. So let's first of all have a closer look at the features of Open SoC Debug. Why do we want to use Open SoC Debug? And of course, you could be, and that's probably the most people here, is somebody that has put together a system on chip, a microcontroller, whatever, and you of course care about all those little nice features of your core that you just created. And then you have this huge pile of things around your CPU core that you also need to get things to work. One, for example, is how do you get actually software onto the memories that you have inside your system? How do you get, for example, a whatever kind of printf output out of this system? Things like that. So all that stuff that you need to actually usefully interact with your system, but it's kind of not your core interest, at least for many people. That's of course not true for me, since I did most of the stuff here. It is extensible, so we use that not only to do debug and trace, but we also use that as a research platform for kind of advancing those areas. So there is a very kind of couple extension points, but it's not extensible to the point that you first of all need to kind of put all things together, because you just have a pile of nothing, but it actually works pretty much out of the box in some scenarios, and you can extend on top of that. You not kind of need to cook your own thing to start with. And you can, and that's a thing that commercial systems don't have so far, you can do debug and trace also beyond chip boundaries. So we have a system and architecture I'll show in a second. If you have, for example, two devices with two CPU cores that are separate, could be kind of two in a package or just two FPGAs, and they're kind of tightly coupled, they're interacting in some way, you're able to kind of see those two devices, or even more, as kind of one system that you want to debug as a whole or trace as a whole, things like that. And it's of course open source, it's MIT licensed. So I like to start with this overview picture, and it's of course intended to kind of be very much too detailed to understand in kind of entirety, but it shows kind of the general architecture of Open SoC Debug and also some of its features already. First of all, we start over here. We have a couple modules. That's the orange things here. And every module has a dedicated functionality. For example, we have here a module that allows us to access the memory of the system, for example, to load your program there or read back whatever happened. Then you have interfaces that go to the CPU cores, for example, if you want to do run control debug or you want to do tracing. And of course, you have those modules a couple times depending on how many CPU cores you have in your system. And up here is one of the central control units. For example, to do a device reset, things like that you also want to do after maybe program loading. All those modules are connected by a what we call debug network. It's in the current implementation, it's a ring network on chip, but essentially you could use whatever you want here. Then you have an off-chip interface, and this off-chip interface also in between here is kind of encapsulated, so you can choose different protocols, different transports that get you across this chip and host software boundary. And I'll get into that in a second. So the project is called glib. On the host side, we have a kind of a mirrored, more or less mirrored structure we have over here as well. Modules, debug modules, they're actually pretty much the same as over there. And I just draw a couple examples. We have, for example, a trace view that just outputs whatever kind of the CPUs did there. We have, for example, a GDB server module that you then connect your GDB to do run control debug. And for example, another one I have here is a Uart emulation, so that you can get for example, the Uart things that you printed and see them here. And I'll get to that in a second. Just the Uart emulation here, not to confuse anybody, is essentially when you want to have not a physical Uart on your device, but want to kind of tunnel the Uart through the debug network, since you have that connectivity already there. And I'll get to that in a second. So first of all, the main building block that Open SoC Debug works on are debug modules, and we'll see them in a sec. Oh, somehow the colors got prettified, so we get some red in there. And the debug modules are all the same. They're the same in software, more or less, or in hardware. It doesn't matter, wherever you instantiate them. And they all have a very common structure. They have a couple of registers that you can some of them are base registers. They're essentially always defined by the specification, and you can add other registers. And you have ways to send events. And this already shows the two types of kind of communication that can happen. You have control communication that happens as a register mapped I/O, and you have event communication, which is just packets that you send for asynchronous data, for streaming data, for example, getting traces off chip, or also, for example, getting an interrupt unsolicited to the host between the modules. Every of those modules has a unique address in the system that allows you to address them. Communication happens, as I said. We have those debug modules, and between debug modules, you can have communication. This communication happens in form of debug packets. They're routable, so they have a source and destination address. And as I said, kind of we have debug packets that are specified for control traffic. That's register mapped control traffic. And you have debug packets which are very loosely defined. You can use those to put, for example, trace or whatever kind of event data into that. The nice thing about those debug packets, you have the same format across all the systems, just like you have an IP packet. So that's actually pretty boring if you look at standard IP or whatever packets, but it's kind of not how tracing systems are doing it today. So you have very kind of specific trace streams and packaging formats that are kind of not transparent when they cross from the device to the host. So then you can use that to just kind of layer those debug packets on top of, for example, NOC packets that will be used to route them on chip. You can layer that on top of, for example, USB 3. And then when you're back at the host, you still have your debug packets and layer them on top of TCP. And now you can communicate in the same way between those modules wherever you are. One thing I mentioned, I think a couple of minutes ago, is the off-chip interface, so between the device and the host. And we do kind of experimentation and work with kind of different FPGAs, and depending on, it's typically FPGAs or also software simulation, and whatever kind of type of device you have. You might have a USB 3 available, you might have Ethernet available, you might have just Uart available or something else. Or if you do kind of a system on chip that you simulate in very later, you might want to have a TCP connection to your simulation. All that is kind of abstracted away by a library that we call glib. And this just has FIFOs on the host side and on the software side, and everything else in between, whatever kind of transport is abstracted away. So if you're ever looking for a way to communicate with your FPGA in an easy way and don't want to care about the specifics of a Cypress FX3 chip and getting that up and running, or even finding the tools to compile their whatever strange firmware, have a look at this project. It's really nice. And FIFOs are easily understandable and it just works out of the box. Okay, so on the changes that I mentioned, as I said, we did a lot of work on the host software implementation. And what we had before was a system that is a bit similar to what kind of CoreSite and Nexus and other commercial tracing systems are doing. You have a very strict separation between the device, which has a modular kind of setup also in for example, CoreSite. So you have modules on the device that have that are attached to the different CPUs and things like that. But then you have a very kind of unidirectional view of the world, since everything that is on the device is now kind of channeled through the trace port or other kind of ports. And then you have on the host side, you have essentially one daemon, one central piece of software that connects to your device. And now this daemon needs to figure out how to actually split this trace stream again, or you can't even split it again. So typically you have, for example, one Lauterbach or one Keil debugger, so there's just one tool accessing this trace port. You cannot really kind of split things between there. But what we would like to have is, for example, you want to have a GDB connected to your device at the same time as for example, another tool just logs the trace stream or things like that. Or another tool kind of logs whatever kind of printf outputs you have. So you have different tools that you somehow need to distinguish between those. And initially we had a system like that was, as I said, kind of very similar to what the commercial tools are doing. So you have addresses for every module that is on the device, and then you have your off-chip interface, and now the host daemon has to figure out how to kind of demultiplex all that data. This works not overly well, since now you are creating this question how to actually demultiplex things. What's actually much easier, and that's what we're doing now, is just make all debug modules really kind of equal. So now you have a really directed communication. If you have, for example, this tool wants to do a memory load, so this has its own address, so this sends its data to the memory access module, this kind of access at the memories, and just sends it to this address, and we're done. What we have now, that's why the addresses now kind of have dot something. There's subnets now introduced, just like in IP networking. So you have one subnet that covers all the debug modules on the host, and one that covers all of them on the device. And kind of having this kind of equal playing field allows you now to go back to what I kind of announced initially. When you now have two chips or pieces of logic that you want to kind of debug at the same time, you just introduce a third subnet, and all the communication still works equally well. Another thing that we did on the host software side is we introduced, and that's probably hard to read from the back, but we have now Python bindings, which make it very easy to create essentially scripts or batch methods, or even extend the system if you want to do testing or using of your device. All the tools we have seen are, so the host software itself is written in C, it's a library. And for example, now if you have here this line here, you have this host controller, so that's essentially on the host, the central communication instance. You have the device gateway, and in this case, you just specify, oh, I want to use the Cypress FX3 connection. In this case, you could use Uart or whatever else, whatever your device essentially has. Then you have this memory access thing, again, as I said, a module, and you can use that to find all memories in the system. Stop all CPUs, that's what we want to do before we do initially kind of hold the reset high before we do loading of the memories. load an ELF file into the system, start the CPUs again, and for example, disconnect. And now if you want to start a GDB server in between, just add 2 lines here and you get your GDB server. The nice thing about that is you also can use it as, since Python has this nice interactive console, you can also use that to kind of interactively interact with your system, which is kind of a programmable, nice interactive way. Of course, not for batch scripting then, but for other kind of just debugging work. One thing that was, or is still in progress, but we started this year, this couple months, whatever, in this Google Summer of Code project. We have Sandeep here, and there he is. Just say hello. So the next work I'm going to present is has been done by Sandeep as part of his Google Summer of Code project. We were pretty strong on, well, reasonably strong on tracing before, since that's what I'm kind of mostly working on. But run control debug, so kind of setting breakpoints, all this GDB interaction was not one of the strong sides. So he worked on the hardware and the software parts for that. And what we have today is the hardware implementation for OR1K, so MR1KX mostly, is working. So this is a register mapped debugging system. This works very well, and this is also easily portable to other ones that use the same technique. The software implementation is not yet completely done, so we are in the review phase of the pull requests there. And one of the future things that we're looking at, so currently we have a 1-to-1 mapping, so 1 GDB server instance to 1 core. There is room to improve that, and I've seen a paper poster outside, and also Jeremy talking about it. So I'm happy to look into that and see how we get, especially when we have the systems that we are typically looking at with 16 or even more cores, how to meaningfully use not 16 GDB instances in that time. Another thing I briefly mentioned is the Uart device emulation. In many cases, you have, for example, if you have a Linux that boots, it boots with a Uart 16550 Uart out of the box pretty easily. And you don't want to add this Uart physically to your FPGA design or your simulation. So the easiest thing is now you already have one off-chip interface, that is the debug off-chip interface. Just emulate this Uart so that Linux can write to the 16550 Uart and thinks it's a Uart, but actually the traffic is going through the debug network. So we have that, and this is also currently work in progress, but it looks really nice. It actually already, so we get the Linux boot outputs already, so this is pretty nice. Good. So that's what happened in Open SoC Debug in the last year mostly. So whenever you have your system on chip design and have your cores there and need actually a bit more debug infrastructure, have a look at that. I'm happy to see issues, pull requests, or of course now questions. Thanks. Yeah.
One of the problems a lot of the debug stuff has is it ends up using a lot of resources on your FPGA, and so like you quickly can't use it because your FPGA is already full with the thing you actually would want to attach to debug. How resource efficient is the Open SoC Debug stuff, and how small can you get it and still be useful?
Okay, so I don't have the numbers on top of my head right now. I can look them up, but what is the fact? So depending on what you want to do, you can go very, very small or pretty large. Very, very small you can get when you just do run control debug, so GDB server integration, since there is almost no logic or any kind of buffers involved. So the network that we have is pretty lean. The buffering is also very minimal. Thing is, it gets more resource heavy once you add tracing. And in this case, the most most area comes from buffers that you need kind of to get the spikes in traffic somehow flattened out. And this is, of course, configurable, and essentially there is no end solution, kind of no ultimate answer. But in the end, the bare system is very, very small. And I'll get back to you with numbers.
Philipp, how does this sounds awfully like what UltraSoC are doing commercially. Is this an open source alternative to UltraSoC?
UltraSoC are great sponsors. I think they're over here. If you're looking for commercial solutions, definitely talk to them. And if they don't have the right thing, maybe have a look at Open SoC Debug.
It's a good thing for learning, right?
Yeah.
So you mentioned you had OpenRISC 1K support. What about other CPU architectures like RISC-V and LM32 and potentially things like Neos or Microblaze?
So the general architecture is written in a way that's pretty agnostic to the individual CPU cores. What we have in low risk, they're using a RISC-V core. What was the current one?
So we integrated the tracing with Rocket.
Yeah, exactly. So essentially, this is essentially an older version of Rocket that we added a trace port to. So we have a working implementation of tracing for the Rocket one. But now in RISC-V and in Rocket, things change rapidly. So there is no defined tracing kind of interface yet. And the run control interface changed repeatedly and still not done from what I know. So I don't know the final state of that.
We integrated with the pulp stuff when it was the same debug interface as the OpenRISC debug interface, right? The advanced debug bridge. So it's everything that's advanced debug bridge can be supported in run control easily. We were also involved in discussions in the debug for RISC-V.
Yeah.
It's definitely on the agenda to get back on track once we're sure it's there everywhere, right? You have it now more or less, right, David? The new debug spec? Yeah. It's definitely on our agenda.
Yeah. So the general infrastructure definitely is suitable for whatever, and different kind of the adapters for the CPUs might need more or less work depending on the CPU.
So just to come back to the how heavy the interface is, just throw a stake in the sand, 450 for LUTs, see if you can beat it. Have some fun. But that's just having fun. Let me come back to some more serious questions. You have some multiple connections in there. I think that's really awesome that you can have multiple debug units connecting to multiple units within your FPGA, sort of a packetized interface as you described it. One of the questions I wanted to ask, though, is why didn't you choose to make the debug modules simple wishbone peripherals and then use perhaps that same wishbone interconnect all the way throughout? And then I'll hold on just a little bit more for one further comment or question.
So essentially, there is...
Oh, you can comment?
Yeah, I'm not sure I completely get the
Yeah, so I can comment. So
question. Maybe you got it better.
So as I made a decision, so we went for NOC because it was the natural choice for us to have flexible interconnects, right? So if you go with a wishbone interface, like the interface is valid, ready data, right? It doesn't get easier in the world. And the routing is very simple that we're using. And we only use rings mostly at the moment. We don't go too much deep into extra hierarchy levels that much, except for the subsystems. So it's much easier than having like a large wishbone something interconnect that in the end is also a NOC, right? So for us it was a natural choice, especially as I'm a NOC person, to do it that way.
But I think the thing is, so if you want to have, so as I said, we have a ring network on chip here as debug interconnect on the chip, but there's no problem kind of replacing that with a wishbone interconnect. Just
it will be a lot of work, yeah.
Well,
It's a design choice. When I worked on something similar, I made a different choice, and so I was wondering why you had made the choice you did. There's consequences for everything one way or another, good, bad, or indifferent.
In the end, kind of, well, the typical systems we have are so there's like 16 or 40 or even 50 debug modules, and you don't want to have 50 masters on your just traditional bus, since they're all essentially masters and slaves at the same time. So you can do that, there's ways of doing that, but in the end, just a ring NOC was kind of a resource-efficient way of doing things.
Go ahead. I was just going to say, that's a fascinating reason I hadn't thought of, is to try and limit the number of masters on the bus. It makes a lot of sense. But go ahead.
that's also where we're coming from. So originally, like it was for the Open SoC project, where we have a massively parallel multi-core processor. So we have like 200 debug modules, right? So and you don't want to put them on a bus, definitely. And what's also important, so this doesn't have the notion of master and slave, right? So it's like all the nodes can send data to each other too. So you can do on-chip processing and all this stuff. So you don't necessarily need to talk to a module only. You can configure modules so that they send data to other modules to aggregate, for example. So you could have a debug subsystem. And we also have modules that make you connect to the debug network from your system bus, for example. So you could receive debug packets in your system to do some kind of on-chip processing or like performance. Or it's also for performance or diagnosis, right? It's not only for debugging.
Final comment, which UART 16550 code did you use? And Stefan knows why I'm asking.
Then ask Stefan.
Yeah, so we wrote a new one yet again. So I started with the OpenCourse one because it was too painful, right? So it's like, it behaves like UART 16550 because we want to use the software that we normally use. So we want to use Linux and just use the normal one. So, but I implemented only what you barely need. It ignores like virtually all, because it doesn't have any serial line. It just sends out package with characters to the host, right? So it's like 20 lines of Verilog code, I think. And I took the freedom not to formally verify it.
There's a question over there.
Very quick one. I guess since you're doing Sapphire IP, you're limited to a maximum of 256 cores?
Yes, currently yes.
Question.
And thank you very much. Coffee break. See you later.